the green light source and hold it up and go through this filter, you will see that it gets a lot dimmer. And not only that, you may also notice that it's actually a little bit of blue coming through. And that is because this green LED is not purely green, but also has a slight bit of blue light in it. Then, the next part is this dichroic mirror. So this one is designed, again, such that it reflects blue light, so you will now not see coming anything through, but if I reflect it to you, you may be able to see that. And then the last part is this emission filter that will transmit the green light and reject the blue light. So in effect, when we would now place these three in this configuration in the microscope, illuminate from this side, go up, we have the objective in the sample here, come back through and go through this emission filter. That's the principle of a fluorescence microscope. These filters, this is exactly the way they are arranged in these cubes that were designed by Ploux, where we have an excitation filter, a dichroic mirror, and then an emission filter here. And so these will, as expected, reflect, and I'll now turn it to you so that you can see it. So the exciting blue light will be reflected to the specimen will fluoresce green, and it will make it to the eyepiece or to the camera sensor. So we've seen now these filter cubes. There's an excitation filter, there's a dichroic mirror, and there's an emission filter. What's very important to know, and the information you should always have about these filters, is their spectra. So what are the wavelengths that are being transmitted, and what are the wavelengths that are being reflected? And those spectra then will look something like as follows, because we have here an excitation filter that passes through this bandpass. These wavelengths, these colors of light, the dichroic mirror is made such that it will reflect everything that is lower than a certain cutoff band and pass through everything that is higher, and then the emission filter will pass through the higher wavelengths but absolutely reject the excitation light. So when you now assemble a fluorescent microscope, your task will be to select filters that match well the dyes that you'll be working with. And what you will be doing in that case is to try to overlay the spectrum of the fluorophores with the spectrum of your filters. So I've here a spectrum of a dye that is probably side 3, the cyanide dye. It excites in the green areas around 550, and it has an emission maximum around 600. So if you now use a bandpass filter centered around 650 nanometers, that will easily reject the excitation light because it's far away from that. But you also note that the integral of it, that it only passes through a fraction of the emitted fluorescence. And it means that you're losing, something like 75% or so of the emitted fluorescence. And in general, you really want to get all the photons that you can, so it's not a perfect situation. So if you now switch to a bandpass filter that is slightly lower, that is around centered around 610 nanometers, then we're catching a much larger fraction, like 75 or 80% of the emitted photons, and we'll be much happier because your image will be much brighter. Now, we'll switch to the lab and show how we're using these filter cubes to collect actual images. Here we have a real fluorescent microscope. So we have a light source back here. This is a mercury arc lamp. Just more the tip of light sources about that. The light then passes through the main body and then hits here the dichroic mirror. So, and I'll show you now how this works. So this is basically a carousel that you can take out. And this carousel contains these same filter cubes that we have been looking at in the lecture. So this one is sitting here. The light hits the excitation filter. I can take these cubes out like this. So the light hits the excitation filter, sitting in the microscope like this, goes through the excitation filter, hits the mirror, goes up, the fluorescence light comes back, makes its way through the mirror, and then here at the bottom, we have the emission filter that goes down and in the end to the camera or the eyepiece. And now, since this thing is motorized, once it's sitting in the microscope, it can, with a push of the button, put in another of these filter cubes. And these cubes have been selected to visualize the dyes that we're interested in. So usually there's one for things like DAPI, for things like GFP or fluorescein, and a cube for something like MGA or rhodamine. Okay? So when I now put this thing into the microscope, and then open the shutter here in the back that blocks the light at the moment, we get blue light coming out of the objective. And when with a push of the button, I put now another dichroic in place. Here we have green light for rhodamine or M-cherry. And if I go on, we have like red light for something like a dye like Psi 5. And so just by switching these, we can select the wavelength of the light for excitation and the filter used for emission, and select the fluorophore that we want to image. So we've now seen how we can use the fluorescent microscope to collect individual channels, images of individual fluorophores. Then what we can do in the computer is put all those images together, give them a nice color, and end up with things like this. So here we have a staining of mitochondria in red, of DNA in blue, and what looks like actin stress fibers here in green. This works very, very well. There are also alternative strategies to doing this. And one is, what you may have noticed in the lab part, is that it actually takes quite a bit of time to move that turret. So going from one position to the other takes quickly, like half a second or so. The turret is pretty big, so it has a lot of vibrations. If you want to go faster, the whole thing starts moving more. Those are all bad things and things you don't really want. So instead of using these filter turrets, what you can do is put your excitation and possibly also your emission filters on a filter wheel. Now, I bought such a filter wheel, and I can show it to you here. So it really is a wheel that has individual filters in them. There's a motor that can, through this rubber band, it moves it around, and we can put, by activating the motor, we can switch between these different filters, and we can do that at a speed that generally is much higher than you can do on a turret. So we then first take an image where we put the first excitation filter in place. So for instance, in this case, we have a blue excitation filter, we get blue light out, we get green fluorescence. Then when we move the filter group to the next position, which has a yellow filter, we get red fluorescence coming out. So we collect now the second image, and that goes much, much faster. Now you may have noticed that there is something funny going on, because this dichroic filter here apparently reflects both the blue light and the yellow light, but it passed through the green light. And so that means that that dichroic filter needs to have pretty special properties, and it's very different from what I've shown you so far. And indeed, that is the case, and luckily the filter manufacturers are able to make such interference filters, so they can make filters that have reflect at certain wavelengths and then pass through the light in between those wavelengths. And some of the spectra of filters you can buy look a lot better than what I'm showing you here. It's really amazing what the filter manufacturers have accomplished, and that has been also a great driving force behind the whole progress in fluorescence microscopy. So we had our image of a red dye, and then we put that all back together in the computer in these multicolored images. Now, also the emission filter, we could, instead of having an emission filter, which would have to be a multi-band pass emission filter, we could replace that by a second filter wheel, and then we have full control and very fast control over both the excitation and emission filters. One practical aspect that you need to be aware of is photo bleaching. So fluorescent dyes don't last forever. They only have so many cycles that they can go through, and over time the fluorescence tends to bleach out. So for instance, in this movie that I'm showing you here, where I coupled GFP to the microtubule tip-tracking protein ED1, we saw that at the beginning we had bright fluorescence, and then over time it completely disappears. Now this is regretfully a common aspect of most dyes, and it is something that we usually really don't like and that we want to avoid. So what can you do about it? First of all, you can select dyes that are resistant against fade, or that do not bleach as fast as others. So for instance, this dye fluorescine that I showed you before tends to bleach extremely, extremely fast. There are now other dyes on the market that have the same excitation and emission properties, but that bleach much, much slower. So you would almost never want to use fluorescine anymore, but use one of these replacements. You can try to label more densely. So each dye has a certain chance that it will photo bleach. So if we now put a lot more labels there, it will not take much longer before a signal is gone. Then, very importantly, you want to change the environment of the dye so that bleaching decreases. So for instance, oxygen is important in this photo bleaching process. So a common strategy is to remove molecular oxygen from your sample as much as possible. For instance, by using glycerol, you're already doing a lot better, or by using enzymatic systems that take out the oxygen from the sample. There are also a lot of compounds that you can add to your mounting medium that will reduce bleaching. And lastly, and very importantly, you really want to use all the photons that you can get out of your dye. So you don't want to leave on an excitation lamp when you're not looking, when you're not observing your sample. So always close the shutter immediately when you're not looking. Or when you're doing camera-based imaging, you want to take the shortest exposure times possible using the lowest amount of excitation light that you can. And you also want to synchronize your camera with the shutter as tightly as possible, so that there's no dead time in which you're not actually collecting the fluorescent light. Now, I'd like to finish this presentation going back to that movie that we saw in the beginning. In the end, they're using fluorescence simply because it's a great tool to let us look at cells and let us look at seminars. And I'd like to welcome you to the iBio course on light microscopy with applications for the life sciences. And in this course, you're going to hear from some of the world's very best microscopists. And we're going to start off with telling you about the theory of light microscopy, starting off with the very basics, but then building up through the course to the latest state-of-the-art techniques in microscopy. But we're also going to try to make this course as practical as possible. So whenever possible, we're going to film at a microscope and show you how these techniques work. And also, I encourage you to listen to these lectures in the course and then find a microscope and use these techniques yourself. But before we go into all of the details of optics and techniques, I'd like to step back for a second and just tell you why I think light microscopy is such an interesting subject and its impact that it's made on the life sciences. So let's even just start with education. For many kids, their most memorable experience, and indeed what often turns them on to science in the first place, is looking through the eyepieces of a microscope and seeing this magical world that was previously invisible to them. And these days you don't even have to look through the eyepiece because you can buy digital microscopes for less than $100. And then kids can use these microscopes to, for example, make movies of amoeba crawling around. And when kids watch these images of amoeba crawling, they get the same sense of discovery and amazement than similar to what Leeuwenhoek must have felt when he first looked at some pond water with his simple microscope a couple hundred years ago. So microscopy is not only good
good for kids, it also satisfies the curiosity of research scientists. And effectively, what the telescope has done for the discovery of the universe to understand the composition of stars and our origins on scales of up to billions of light years, the microscope has done for biology on the scale of nanometers to microns. And the human brain is incredibly good at processing images and extracting information from them. So when we look at these images of life, of cells, we can extract information and deduce ideas of how these living systems work. That's so very powerful. And these microscopes also transport us into this incredibly beautiful world that isn't visible to the naked eye. And what I'd like to do right now is just to step off the screen for a second and give you a tour of what you can see through the microscope. Not only does the microscope make these beautiful static images, but if you put a CCD camera on a microscope, it can take action movies of life. And as a famous American baseball player and also philosopher, humorist, Yogi Berra said, you can observe a lot just by watching, such as watching these images here of chromosomes in a cell undergoing cell division. And indeed, making movies gives you information both in time and space of how living systems work at all kinds of different scales. So for example, here we're watching a movie of single molecules moving around in the membrane of a T cell. And at another scale here, you're watching T cells moving through an intact lymph node interacting with other cells in that lymph node. In other movies, for example, here is you're watching microtubules in green and actin in red undergoing all kinds of complex dynamics in a cell. And at another scale, we can look at these cytoskeletal systems in an intact embryo, for example, in the fly here, where you can watch synchronous cell divisions taking place in a living embryo. And from all this dynamic information, it gives us tremendous insight into how living systems work. Let me take you back a little bit just to tell you what microscopy has done for the biological sciences over time. So let's go back now to the 17th century. And here is Robert Hooke's simple compound microscope, which he turned to look at plant tissue. And what he saw was these repeated structures in here that reminded Robert Hooke of the cells in a monastery. And in fact, based upon that, he gave them the name cells, a name that has stuck to this day. And a contemporary of Robert Hooke was Van Leeuwenhoek, a Dutch microscopist, who turned his single lens, an amazing single lens microscope that he put in front of his eye, and viewed a little drop of pond water and saw that this little drop of pond water was crawling with all kinds of moving creatures in it, creatures that he called animalcules, which we now know to be protozoa. He then extracted material from teeth, and I think dental hygiene wasn't that great in the 17th century. And from that material, he actually discovered new organisms, which we now know to be bacteria. Now, moving ahead a couple centuries, microscopists then used the microscope in combination with various dyes to pull out new features and details of the inside of cells. For example, here is Walter Fleming's studies of cell division, where he used an aniline dye that stained all these fascinating structures, which are chromatin and chromosomes. And in fact, the word mitosis, which he coined, is from the word thread, based upon these thread-like fibers that he saw. And in addition to the chromosomes, he also saw all these fine structures now, which we know to be microtubules that make up the mitotic spindle. So this image that you see that was done in the 19th century looks remarkably like a modern textbook drawing of mitosis that you would find today. Now, other scientists at the time experimented with other kinds of dyes and stains. Camillo Golgi used a silver stain and found new structures in cells, one of which was named after him, which is the Golgi apparatus. He also used these silver stains to study the nervous system. And a scientist, Spanish scientist, who also used the silver stain developed by Golgi to explore the nervous system in vast ways was Ramon y Cajal. And here are just these amazing drawings of what he saw under the microscope, categorizing all the different kinds of cells that make up the brain. And both Cajal and Golgi shared the Nobel Prize in 1906 for these discoveries that they made with the microscope of the nervous system. Now, these stains give these beautiful images, but you have to fix and kill the cell to make them. And there's a new appreciation that you can get all kinds of new kinds of information about the dynamics of living systems by not killing them, but making a movie of them in action in real time. And this is work by Shinya Inoue, and you can hear his work on this subject in the iBio magazine piece. But he developed new microscopes that use polarization microscopy to study cell division and could see all of these movements of chromosomes and the behavior of fibers. And from these movies, he was able to deduce an amazing amount of information on how mitosis works well before the molecules that make up these structures were known. At about the same time, also, Hugh Huxley and Andrew Huxley were using microscopes to study muscle contraction. These two are unrelated, and they worked on this independently. And here is an image of a muscle, a sarcomere, with phase contrast microscopy. And you can see all of these distinct banding patterns here. And this banding pattern changes over time during muscle contraction. And from the behavior of this banding pattern seen under the light microscope, they could deduce the sliding filament theory, which is how muscle contracts. And you can learn more about this in another iBio magazine piece from Hugh Huxley. Now, my own experience with light microscopy came when I was a graduate student in the 1980s. And I was interested in the process of how proteins and membranes are transported in nerve cells. Basically, nerve cells are remarkably long cells. They have a cell body that's present in your spinal cord, and then they can extend a really long axon that may go all the way to the tip of your foot where the nerve terminal is. And the question is, how does this transport system work? Well, the way this was studied in the 1960s and 1970s was to inject radio-labeled amino acids, which were incorporating to regulate proteins in the spinal cord, not in a human, but in a rat. And then what these scientists had to do was wait some period of time, take the nerve cell out of the rat, and chop it up into little tiny pieces, and then see how far that radioactive protein traveled in the axon. Now, from this, they could get speed of transport, but you can imagine it was an incredibly laborious process. It would be much better just to observe all this transport with a microscope in real time. And that opportunity was afforded with a new revolution in light microscopy done independently by two investigators, Robert Allen and Shinya Inouye again, who now put a camera on a microscope. So instead of viewing it with your eyes, you can now view it with a camera. And they also use computers to enhance the contrast of those images to obtain new remarkable movies of the inside of living cells, such as this movie here from Allen and colleagues of the interior of an axon, where now you can see directly, not with radioactivity, but by direct observation, all of these little organelles that are moving up and down inside this axon, and big objects such as mitochondria over here, giving a whole new insight in even about 5 minutes of observation of how this transport process works. Now, also, you can use the microscope to watch proteins in action, effectively watching biochemistry. So this is my own work looking at an enzyme, an ATPase kinesin, transporting plastic beads along microtubules. And from this, you can get all kinds of information on how this protein works. So now, previously, biochemistry was only done with spectrophotometers or radioactivity, but now you can use microscopy as a tool for biochemistry as well. And the microscope not only helped biochemistry, but it also joined forces with genomics with the discovery of the green fluorescent protein. And this was work done by Shinomura, Chalfie, and Chen. There is an iBio magazine piece by Marty Chalfie that describes the discovery of GFP, and these investigators won the Nobel Prize for this discovery. The green fluorescent protein comes from a jellyfish and is fluorescent. So now you can fuse the GFP protein to any protein in the genome and follow the dynamics of where that protein is and how it behaves in space and time, giving a whole new aspect of discovery to how proteins behave in living systems. Now, microscopy, even at this moment, is continuing to advance in a remarkable number of ways. Microscopes, first of all, are getting much more complicated so we can do more types of processes. And no longer is microscopes just about optics. It's about electronics, robotics, and software. Now, most microscopes work in conjunction with a camera that captures the image, but the microscopes are often robotic themselves. They have automated focusing devices, they have stages that can move, and all of this is controlled by software. And this just even shows an example of a fully automated microscope where a robotic arm will pick up 96 well plates, put it on a microscope stage. The microscope then does all the work. It automatically focuses, it takes snapshots of what's on the specimen, it moves around to different locations on the slide, and all that information then can be captured by a computer. Now, microscopy is also getting into new realms that were thought to be impossible. So here's a famous microscopist, Ernst Abbe, that you'll learn about in the course, and he came up with a famous formula for the resolving power of the light microscope, which is basically the distance of how far apart two objects are where they can still be distinguished as separate objects. And here's his equation, which was thought to be so immutable that it was carved in stone in this memorial to Ernst Abbe in Germany. But now there are all kinds of techniques that are breaking this resolution barrier, techniques that are called super resolution microscopy that are really exciting and you're going to learn about in this course. And here's just an example of a fabulous image of the front of the cell taken by Jiawei Zhang showing the actin network. And this to show you how remarkable this technique is, here is an image of that actin network at the same scale over here, taken at the top here with conventional epifluorescence microscopy where you can see hardly any detail. And here's the same field here of actin now taken with super resolution, where the color coding is also showing z-axis information as well. Now, the microscopy, super resolution microscopy, also involves a computer to generate those images. And indeed, computers are joining up with the microscope in all kinds of new ways to quantitatively analyze images. So here, for example, is the leading edge of a migrating cell here, and all of these little colored dots here are information that's being extracted out of this image by a computer, which is giving information on the behavior of the actin filaments and also traction forces that this cell is feeling. So computers now can analyze images in ways that are very hard to do with the human eye. Now, not only is the microscope also good for taking the images, but it can also be used for actually manipulating objects and molecules in cells as well. So, for example, here is a technique called optical trapping that you'll learn about. And here the optical trap is capturing various beads here and controlling their position, making them move in this little computer-controlled dance. And on the bottom, what you see here is a way in which light through a microscope can be used to control protein-protein interactions in the cell. And these little yellow flashes that you see here are regions where a flash of light is put in the microscope to induce a protein-protein interaction and cause the cell, as a result, to migrate in a new direction. So as you can see, microscopy is making breakthroughs at all scales of biology. At the level of single molecules, you can see the fine details of how these machines work. Here's a movie of a kinesin molecule in animation showing its two enzymatic domains walking along this microtubule track. And you can actually see this with a microscope. You can tag one of these blue heads with a quantum dot and then watch this quantum dot labeled kinesin moving along microtubule tracks here. And you can analyze this motion with a high degree of spatial accuracy. So if you follow the position of that quantum dot, you can see, in fact, these individual blue heads taking these discrete steps as it marches along the microtubule. And at a whole different scale, we can also look at the complexity of very large three-dimensional tissues. And what I'm showing you in this movie over here is a tour of the brain, of a mouse brain, done with a technique called array tomography, which you'll hear later about in this course. It's showing you this beautiful, complex, three-dimensional pattern of neurons that is present in the mouse cortex. So with this perspective, and also introduction to the history of biology, let's get into the course and let's learn microscopy. Thank you. cells that were crawling around in his mouth. But these are bacteria. And so Leeuwenhoek was able to